And Newton's method is a way to approximate the zeros of a function. So there are a lot of things that Newton did, clearly. This is one of the coolest, I think. That he was able to find a way, given any random function, to use linearizations, to use tangent lines, to approximate that zero of that function if you don't know what it is. And so you can get to a very, very high degree of accuracy for the root of a function in just a few iterations of this formula that I've got down below. That we're gonna prove this formula here in just a second. So what Newton said was, well, suppose I have some function. We're going to come back to this page in a second. But suppose I had some function that has an x-intercept. There's a function with an x-intercept. You guys agree with that?
Yes.
Yes, good. All right. So that function has an x-intercept. He said, suppose I guess what that x-intercept is. All right, I'm gonna take a guess, and I'm really bad at guessing. So I'm gonna guess that the x-intercept was this value right here. Pretty good guess, huh?
Of
course. The answer should be no. It's a horrible guess. We're gonna call that our first guess, or our initial guess. We'll call this x naught, x sub 0. Is that the actual x-intercept of this function?
Nope.
What was that? Was that a yes or a no?
No.
Oh, good. It sounded like you said yup or something weird like that. All right. So this is not the correct x-intercept. So what Newton said was, well, here's what I'm going to do. I'm going to take this value, this x value that I came up with, and I'm going to go up here onto my function, and I'm going to find the coordinates of that point. So suppose this function is the function f of x. What would the coordinates of this point then be? They should be x naught, comma, f of x naught. Do you guys agree with that?
Yeah.
Yeah, all right. Does this function have a tangent line at that point?
Yes.
Yeah. Could I draw that tangent line, and could I also find the equation of that tangent line? Oh, that's not very good looking. There's the tangent line to that function at that point. Do you guys agree? Could I find the equation of it? How do I find the equation of a line?
You have a point and you find the slope and you put them
Right.
together.
Exactly. A point and a slope, you use point slope form, write an equation. Easy, right? Well, what's the slope of this line at that point?
F prime of x naught?
Yeah, it's just the derivative, right? The derivative tells us the slope. So the derivative at x naught is the slope of that tangent line at x naught. So we have the point x naught, f of x naught, and the slope f prime of x naught. That would give us the equation, what? Y minus y1, which is f of x naught, equals m, or f prime of x naught, times x minus x naught. Everybody agree that that would be the equation of that line? Y minus y1 equals m times x minus x1. Yeah, I hope. Everybody good with that or no?
Wait, could you explain again why it's x minus x naught over there?
Yeah, so it's y minus the y value, and then it's m and x minus the x value. So the x value of the point is x naught, so it's just x minus x naught. Y minus y naught, or the initial y value, f of x naught. And then f prime is your slope. So x minus x naught, x minus the x value.
Wait, isn't this the linearization formula?
Yeah, it is. Right. F of a plus f prime of a times x minus a. Yep, exact same thing. So I mean, that's how we came up with it, right? Is we wrote the tangent line equation to some function, right? At a. That's exactly what we did. So yeah, it's the same exact thing. Everybody good with that equation or no? Okay, I'll assume that's a yes. Does this tangent line have an x-intercept?
Yes.
Yeah, it's right here. I'll call that x1. Could I find the value of x1?
Yes, because you have the equation.
Right, we have the equation of the line, so we should be able to find x1 because what do we know about y at x1?
It equals 0.
It equals 0, right? Because that's an x-intercept. So we have 0 minus f of x naught equals f prime of x naught times our x value, which this x value is x1 minus x naught. So if we solve this equation for x1, we should have the value of x1. So let's do that. That gives us a negative f of x naught, right? And then we're going to divide that by f prime of x naught. And if we want x1, that just is leaving us with x1 minus x naught, so we can just add the x naught over. Everybody agrees that's what you'd get if you solve for that x-intercept for x1? Yes, no, maybe?
Yeah.
All right. Well, is this the x-intercept of my function?
No.
No. Is it a better approximation of it than x naught was?
Yes.
Yeah, it is, right? Okay. Could I find x1 comma f of x1? And does it have a tangent line? And could I write the equation of that tangent line?
Yes.
And could I use the equation of that tangent line to find the x-intercept of that tangent line?
Yeah.
And could I call it x2?
Sure.
I think I sure could, right? Is that a better approximation for the x-intercept of my function than x naught was and better than x1 was also?
Yes.
And couldn't I just do that again? And wouldn't that give me a better approximation? And couldn't I just do this as many times as I wanted to until I could get to whatever degree of accuracy that I wanted for the intercept of that function?
Yes.
Isn't that cool? You can just use this linearization over and over and over again and a little bit of basic algebra to get literally as close to the actual value of the x-intercept of any function that you want, as long as you've got an interval on either of it that you can take the derivative of it at. It's pretty impressive. It's one of the coolest things I think that Newton ever did, really. And we'll note that this formula right here, x naught minus f of x naught over f prime of x naught equals x1, is pretty straightforward to solve. All you need to know is a guess, a number, right? You need to know the function and you need to be able to take its derivative, and you should be able to find the next intercept. And then you could just plug that one in and find the next intercept, and then plug that one in and find the next intercept, and so on until you are as accurate as you wanted to be. And that's what this formula right here is saying. X sub n plus 1, the next x-intercept, is the previous x-intercept minus f evaluated at that x-intercept divided by f prime evaluated at that x-intercept. And that's what we're doing, is we're just repeating that process over and over and over until it's accurate. Everybody good with that? Any questions on that? on that process, the idea of what we're doing there?
How would you go ahead?
Oh, okay, thanks. So I'm assuming this like helps with just like estimating. Is this kind of related to when you want to find an estimate, when you like want to choose a value that fits really nicely into an equation? Is that somehow related to that? Because what I'm confused
Yeah,
about,
I mean, yeah, it could be for sure.
okay.
But it doesn't necessarily have to. I mean, it's also just, sometimes we just want to know the x-intercept of a function. And it's really just another use of linearization to be able to find a very good approximation for the x-intercept of a function. Because there are some functions that we just can't, we can't solve algebraically for setting it equal to 0. I mean, you make some really horrible, disgusting looking function that you just can't solve. Well, you can always, if you can take its derivative, you can always get a very, very, very good approximation of it, accurate to as many decimals as you need by just repeating this process over and over again. So that's the main reason for it. Sometimes we need to, sometimes you come across a third or a fourth degree polynomial that you just can't solve, right? Well, you could use this process to approximate that root very accurately. And in real world situations for things that are being modeled with complicated functions, this is a good method to approximate, the zeros, and those zeros become maxes and mins, and those have real world applications, which we're going to see later today. On another note, what your calculator does when you ask it to find the x-intercept of something, you plug in the graph and you say find the x-intercept of it. Well, this is literally what it's doing. It's using this idea of tangent lines to the curve at all these points. It's just doing the calculations very quickly and coming up with a very accurate response for you almost instantly. So they're just using this formula in your calculator, basically. Does that answer your question? Does that help?
Yeah.
Cool. Somebody else had a question too? Or maybe I've already answered it now. I don't know.
How would you know when to stop using it? Like, because you can use it over and over, right? So how would you know at what point would you stop?
Well, so if I say I want it to be accurate to 4 decimals, well, as soon as you get a couple of results in a row that have the same first 4 decimals, you're good. We're going to use our calculator to help us to evaluate these because they become very unpleasant. And when we use the calculator, I'm going to say either have it accurate to 9 or 10 decimal places. So we'll see that right now. We're going to use Newton's method to solve this function, x cubed plus 3 plus 1. So this is just a cubic, right? That can't be factored by grouping. True? Can't factor that by grouping?
Yes.
Okay. And the only possible rational roots of it using the rational root theorem are positive or negative 1, because this is 1 and this is 1 or negative 1. This is got factors of 1 or negative 1. You divide them, you get 1 or negative 1. If you plug 1 into it, do you get 0?
Nope.
No. And if you plug negative 1 into it, do you get 0?
Also no.
Also no. So this does not have any rational roots. It has an irrational root to it. And so we want to see if we can figure out what that is and get a good approximation for it. So first off, we need to figure out an interval on which that root should occur. On what interval do we think that root should occur? We could probably use what theorem to find an interval?
Oh, would it be Rolle's theorem?
It would not be Rolle's theorem, but that's a good guess. Nah. Because remember, Rolle's theorem is telling us we have a place where the derivative is equal to 0. We're looking for a place where the function itself is equal to 0. So this one is going to be intermediate value theorem. Somebody said it. No, not squeeze theorem either. Intermediate value theorem. So we're going to use the intermediate value theorem, and we're going to say that this function is continuous on all real numbers. And if it's continuous on all real numbers, if we can find an x value that it's negative at, for example, like f of -1, what's f of -1? -3. And if we can find an x value where it's positive, like at 0, we know that since it goes from negative to positive and the function is continuous, the intermediate value theorem says there must be a solution to this equation on the interval from -1 to 0. Everybody remember the intermediate value theorem now?
Yep.
Oh, good. All right. So anybody have a first guess that they want to try between -1 and 0? Valued like x not to equal.
0.5.
0.5 is not between -1 and 0, but we could do negative.
Oh, wait,
0.5.
shoot, -0.5.
Yeah, that'll work. -0.5 will be fine. Yeah, right in the middle of them seems like a good value to start at. So now we need to write out this formula. So the next intercept that we're going to try ought to be -0.5 or x sub n minus f of x sub n divided by f prime of x sub n. Well, what's f prime of x? (3x squared plus 3). So 3x sub n squared plus 3. Good or no? Everybody good that that's the formula we're going to use? I hope. All right. So what you're going to do is you're going to take out your graphing calculator, and we're going to use our calculator to evaluate this for us. So first thing you're going to do is you're going to just type in -0.5 because that's our first guess and hit enter. What that's doing is that's storing that as your most previously used answer. And you guys are familiar, I hope, with the answer button, right? If I just hit +6, it will be, it'll use that previous answer. Or if I do something like the natural log, I could do the natural log of the answer, and it'll just use that previous answer of 5.5 that I now have and take the natural log of it. So everybody, I hope, is good with that. Yeah. So we're going to type in -0.5, hit enter, store that as our most recent answer. And then anywhere in your formula where you see an x, you're just going to replace it with answer. So our formula starts with x sub n minus, right? So we're going to just do answer minus. And then we got a big fraction. So we'll start a parenthesis for the fraction, start a parenthesis for the numerator. And we're going to type in it's x sub n cubed. So we'll type in answer cubed. And then what is it? Plus 3x sub n. So we'll type in plus e answer. And then it's +1, so we'll type in +1. We'll close our parenthesis for the numerator, divide for our fraction, open a parenthesis for our denominator, and do the same thing. It's 3x sub n squared, so 3 answer squared plus 3, and then close the denominator's parenthesis, close the entire fractions parenthesis, and hit enter. And it tells us that if you plug in -0.5 to that, you get looks like -1/3, right? -0.3 repeating. So x sub 1 is -0.3 repeating. How many times do you think it's going to take to get the right answer or the close enough answer? That's right, not very many. All you have to do now to get the second one is hit enter. It'll reuse -1/3, and it gives you -0.32 repeating. So x sub 2, -0.32 repeating. Everybody good so far? Hit enter again. You get this. What was that one? negative 0.322, what was it, 1,85355. And go hit enter again. You get this. Hit enter again, look, it stays exactly the same. So it didn't take that long to get us to 10 degrees of accuracy on our decimal. So this one was x sub 4 equals what? Negative 0.322, what was it? 1853546. And x sub 5 equaled the same. And therefore, we are now at 10 degrees of decimal accuracy. And that's a good answer. And amazingly, to get to 10 degrees of accuracy, only took us 1, 2, 3, 4 things that we plugged into it. Any questions or issues with that? Everybody good? Everybody still alive?
Yes.
All right. Would we like to do another one, or do we feel okay about that? You're gonna have an assignment where you need to do some of these tonight. So
Can we do another one?
of course. All right. Let's do another one. Anybody got a function they particularly want to use? I guess that's a no. All right, here's the function we'll use. F of x equals x ln x squared minus 1. We want to find the root of that function. I'm going to be kind to you this time. I'm going to say we want to find the root that is on the interval between 1 and 2. Oh, sorry, Cassandra. I didn't see you type that in the chat. We're going to do a more complicated one. X squared minus 3 would have been fine also. Although we should know that that should be square root of 3 and negative square root of 3, right? All right, we're going to use this one. I don't know. X ln x squared minus 1. So first off, if it's on 1 to 2, what do you think your initial guess ought to be, or what's a good value for your initial guess? How about 1.5? And then our function has a derivative of what? Got to use the product rule for the x ln x squared. So that'll be x times the derivative of ln x squared, which is 1 over x. Oh, I don't know why I wrote that like that. Which is 1 over x squared times the derivative of x squared, which is 2x. And then plus ln x squared times the derivative of x, which is just 1, and then the minus 1 goes away, which simplifies down to 2 plus ln of x squared. Everybody agree with that derivative?
Yeah.
All right. So our formula, x sub n plus 1 ought to equal x sub n minus f of x sub n, so x sub n ln x sub n squared minus 1 over 2 plus ln x sub n squared. Good or no?
Good.
All right. Let's plug it into the calculator. So we're starting at 1.5, right? That'll be our answer. We'll do answer minus parenthesis for the fraction, parenthesis for the numerator, x, oops, not x, answer. Function is x, and then ln of x sub n, answer, squared. Close the parenthesis on your ln, minus 1. Close the parenthesis on your numerator, divided by parenthesis on your denominator. And then what was our derivative there? It was 2 plus ln of x squared, I think. Is that right? So 2 plus ln of answer squared. Close that parenthesis. Close the parenthesis for the denominator. Close the parenthesis for the entire fraction. Hit enter. We get 1.423016472. 42153051. Oh, there we go. Still different. And then right there, it repeats the exact same thing. And so we end up with 1.421529936. So we had our initial guess, x0, x1, x2, and then 3 and x4 were the same. Right. Normally, I'd ask you to write them all out. But I won't today. 1529936. Good or no? Everybody feel all right about that? Pretty straightforward.
Wait, so if we had a quadratic equation like Cassandra's, would we have to use it twice to find both roots and approximate them?
Yeah, so I'd either specify a specific interval, or if I said find them all, you'd want to know that there's 2, yeah. But chances are I'll only ever ask you to find one. I'll just say, hey, find the one on this interval, or if there's only one, I'll just say find it. Good or no?
Good.
All right. So tonight you will have an assignment on Newton's method. I'll post it up just shortly after class today. But we're going to move on and start talking about the next topic now, which is optimization. So we're going to start with some very, very basic, almost word problems. Then we're going to move into some actual word problems where we're applying these ideas of the first and the second derivative tests and maxima and minima to some somewhat real world situations. So take a second, read through our steps that we're going to be using whenever we do optimization problems, and we're going to talk about them and take a look at what the problems are like. So take just 1 second and read through that, and then we will talk about it. So an optimization problem is just a problem where we are looking to maximize or minimize something, right? It might be a distance, it might be a volume, it might be a length, it might be, you know, a radius, it might be an area, it might be a surface area, any number of things, it might be a cost. Okay? So we're trying to minimize or maximize something. So sometimes it will require a bit of reading through the problem multiple times to figure out what's going on and to sort of understand what you're supposed to be doing. But in all optimization problems, you're always looking for a max or a min of something. So I recommend that you always draw a picture and label it as best you can. That ought to help you to write the equation that you're going to need to write. So you'll write an equation for whatever thing you're trying to maximize or minimize, and then you'll get it all in terms of one other variable. Sometimes graphing that equation and looking at its domain will help you. And you definitely always want to keep in mind what the domain of whatever equation that you write is. Once you have your equation, suppose we're looking for a cost. So once we have an equation that reads as cost equals something, all in terms of x, you're going to take the derivative and find the critical values of it. And then you're going to look and see if they're maxima or if they're minima. And we'll do that by taking the derivative and setting it equal to 0, seeing when it's undefined, right? Looking for those critical points. Does that sort of make sense what we're going to be doing?
Yeah.
Okay, let's give it a shot. So we're going to start with one that's not really a real world situation, but it's going to give us the idea of what we're doing. We're going to look for the point on the graph of y equals x squared plus 1 that is closest to the point 3, 1. So first question is, are we trying to find a minimum or a maximum of something?
Minimum.
Right, we're trying to find the minimum what between this function and this point?
Minimum distance.
Right, this is telling us we want a minimum distance. So what we need to do is we need to write an equation that represents the distance between those 2 points, or between that point and that function. So first, let's draw a picture. And in this case, our picture is just going to be the function, x squared plus 1, and the point, 3, 1. Clearly, the point 3, 1 is not on that function, so we know that the distance is going to be, the minimum distance is certainly not going to be 0. It's going to be greater than 0, right? And the way we find that distance is, what formula do we use to find the distance in 2 things? What's the formula to find a distance? That formula is called the distance formula, right? You should know the distance formula. Distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. Everybody good with the distance formula?
Yes.
All right, what do we need to do the distance formula? We need 2 points, don't we? There's one of them, 3, 1. What's the other point?
The one we're looking for.
The one we're looking for, yes. And generically, what is that? It's some x comma y. It's some ordered coordinate pair, isn't it? I mean, isn't that what we're looking at? 3, 1 and some ordered pair x comma y, where y is equal to what?
F of x1.
It's what?
It's like f of x1, so x1 squared plus 1.
Yeah, x, yeah, you don't need to call it an x1, we'll just call it x. But yeah, where y is equal to x squared plus 1. So our 2 points are 3, 1 and x comma x squared plus 1. Right? It's just an xy where that y value has to be on this parabola. So our distance formula should be the square root of x minus 3 squared plus x squared plus 1 minus 1 squared. Or what does that come out to be? The distance should be the square root of, this one we can expand out easily enough. This one is just x squared squared, so x to the 4th plus x squared minus 6x plus 9. Everybody good with that or no? Any questions there? Okay. And we want to find out when is this distance at a minimum. So how do we figure out when a function, in this case, a distance function, is at its minimum?
We take the derivative.
Take the derivative and see when it has critical values. So what is d prime equal to? Well, this is the square root of u, so it ought to be 1 over 2 root u times the derivative of u, which would be 4x cubed plus x squared. Oops, sorry, plus 2x. I don't know, I wrote x squared plus 2x minus 6. And we could simplify that out if we wanted to by factoring out a 2 and then dividing the 2. Right, that's 2x cubed plus x minus 3 over root x to the 4th plus x squared minus 6x plus 9. And what do we want to know? We want to know when that's equal to 0 and when is that undefined. So first off, d prime equals 0 if the numerator is equal to 0, which what was our numerator? X cubed, or is it 2x cubed? 2x cubed plus x minus 3, right? Oh, that 2 is atrocious. 2x cubed plus x minus 3 equals 0. And d prime is undefined if equals 0. That's square root of x to the 4th plus x squared minus 6x plus 9, right? Well, first off, let's think about what would happen if this was equal to 0. If the square root of x to the 4th plus x squared minus 6x plus 9 was 0, what does that tell you about the distance? If this denominator down here is equal to 0, then the distance must be
0 as well.
0 as well, right? Because if that thing is 0, well, then that's the same as what we've got there. Is the distance between that point and that function ever 0?
No.
No, because that point is not on the function. So we'll say this is never true because d never equals 0. All right, now what about this one? When is this true? Well, we could use the rational root theorem to try and figure it out, right? What are the factors of -3? Positive or -1 and positive or -3? And the factors of 2 are positive or -1 and positive or -2. We could use synthetic division to divide out and see which of those works, right? 1 over 1, 1 over 2, 3 over 1, or 3 over 2. Anybody have one they want to try?
1.
1. Okay, what a great guess. So 2x cubed, 0x squared, 1x minus 3 are coefficients going across. 1 is the one we're going to try, or 1 over 1. Bring down the 2, multiply by the 1, add, multiply, add, multiply, add. If it comes out to 0, then we're good. So this became x minus 1 and 2x squared plus 2x plus 3 equals 0. So x equals 1. And then what about this one? I don't see a nice way to factor that. So -2 plus or minus the square root of 2 squared minus 4 times 2 times 3 all over 2 times 2. What's happening inside that square root with the discriminant b squared minus 4ac?
It's negative.
It's negative, meaning there are no real solutions. So the only possible place where we could have a minimum is at x equals 1. Everybody agree with that?
Yes.
All right. So then what we need to do is we need to make a line chart with x equals 1 on it, plug in a value less than 1, like let's say 0 into our derivative. Here's the numerator of our derivative. If we plug in a 0 to that, it becomes
Negative.
negative, and a square root will always be positive, right? So a negative over a positive is a negative, which tells us our function is decreasing. And if we plug in something more than 1, like 2, well, the square root's always going to be positive. And then this, if I plug in 2, becomes what? 16 plus 2 minus 3, which is definitely positive. So we can see that we definitely have a min of our distance function at x equals 1. So we'll just go back and we will figure out what's f of 1. Well, our function was x squared plus 1, right? So that'd be 1 squared plus 1, which is 2. And the minimum distance is at the point 1 comma 2. Good or no? And if I asked you what was the actual minimum distance, you'd go back to your distance function, which would be the square root of 1 to the 4th plus 1 squared. What was it? Minus 6 times 1 plus 9. And we would find that the actual distance was 1 plus 1 is 2 minus 6 is negative 4 plus 9 is 5. We'd actually have a distance of square root of 5, and that's the distance between the 0.12 and the 0.31. Good or no?
Makes sense.
All right. I would love to get started with the next one, but I think it's going to take us more than 10 minutes to get through it, and I don't really want to keep you guys afterwards. And since I'm not giving you an assignment on this, it's due till Friday or so, Thursday or Friday. I think we can hold off and do the next one tomorrow. Any questions on anything we've done today?
For the Newton's method, do you want us to write out like each of the numbers with the decimal?
Yes, please do. Yeah, so just like I did it on the first one. I know I didn't on the second one because I got to keep going back and forth from one screen to the other when I'm doing it, but I'd like to see this each time. So when you do Newton's method, I want to see, number one, how did you pick your value that you started at? Number two, what is the formula that you're using? So what's the derivative and then what's the formula you're using? And then show me all of the values until you get two that are the same.